Hey.
What's part 2 release?
What's that?
Is part 2 released today or?
Yeah.
It's up there.
Yeah, I just have to post it on modules, but yeah. If you go to files, you're going to find it. I'll add it to assignments later. All right, so the concept behind AdaBoost is that you start with a simple weak classifier, and then you try to find the points or the samples that that classifier does not predict correctly. Okay? And then you try to give more importance to those misclassified samples. And you do the same thing again and again until a certain rounds. So there is some theory behind it. You're going to see that the weights have a certain expression. And in the homework, I linked the paper, so you can go back to the paper to understand why those weights exactly. But the idea there is that they are exponentially increasing. So each time we multiply by a certain value. So we're not adding, okay? And this is different from bagging. In bagging, you basically, each learner will be trained on a specific subset of the samples. In random forest, there are two options. You either fit a subset of the features, which is the columns in this case, or you project. So the initial random forest was about projection. Let's say you have 100 features, you're going to project them onto a subspace that has 10 dimensions. So basically you end up with 10 features. That's the initial one. Later, they just started subsampling. So say, okay, I have 100 features. I'm just going to pick 10 of those and train each learner on 10 of the features randomly. Okay? And you can show that in expectation, if you just pick random features, it's equivalent to projecting on subspaces. So that's another thing. And it's much computationally faster, multiplying by matrix. I mean, you have to generate a random projection, and then you multiply by it. It's way slower than just picking a random subset of features. So in the homework, we go with the original one, with the random projection, because last semesters we did these subsampling features. So we just wanted to try something different. For AdaBoost, as we said, we're going to work on weak learners. We're going to pick just the digit data set that you have already seen, but in this case, it's a binary classification, so we just pick 3 and 8, because they're usually very similar, okay? Okay. All right, so in this data set, we're going to have a train and a validation part already shuffled. So in this case, we can just plot something. Let's pick another number. Yeah, it's either. You're going to have different results from me depending on the index and the shuffle that you get. Okay. So AdaBoost in theory works on decision stumps. So basically a decision tree with depth 1. So you remember last time we had a tree that's really deep. So in this case, a decision stump, it means that you only have one root node and 2 children, one left and one right, nothing more. But there's nothing that prevents you from using any type of weak learner, okay? And yeah, so in this case, let's just take a decision stump H and let's fit it on our training data and see how it performs on the validation, okay? All right, so you're getting around 85% accuracy, not bad. And I also want to check what's the distribution of the labels. So let me just do MP unique data y train, return counts equal true. Yeah, so training is 50% train, Let's look at the valid. Yes, the same. So we have the same balance between 3s and 8s. Okay, so this notebook is based on previous class, I think 2019. So they had some sort of explanation of AdaBoost that assumes that you already seen it in the lecture, which is not the case for you. So I changed it a little bit, but I'm not sure it's even clearer than before. But I'm going to explain everything. Okay. All right, so the AdaBoost needs a number of rounds, or you can call it number of learners, since that each round you're creating a new weak learner. Then we need the base classifier that we're going to use. In this case, it's going to be decision stump and random state. All right. So the alphas is the vector it's an array where we're going to put the weights for each learner. Okay. So assume we have 2 learners. One has weight 1, the other one is 10. So if the second learner predicts label 1, it's always going to win. Okay. But when you have multiple ones, you might have one that has weight 10, but the sum of the others is more than 10. So there's some kind of a weight war there. Okay. So in the fit function, so what happens is that at each round, we're going to train a new learner. And then we're going to use all the learners that we have until that step to predict the labels. Once we do that, we're going to see which of those samples have been misclassified. So we are going to increase the weights for samples that are misclassified. Okay? So the later learner is always biased towards the misclassified samples. Okay? And the trick there is that sometimes you have outliers in the data set. So if you train for a large number of rounds, eventually the outliers are going to have larger weights than any other samples. So the later learners will just concentrate on the outliers. Okay. So luckily for us, we're just going to do binary classification. So we're not going to have any fancy manipulations of those weights. Okay. And to make it simple, we're just going to associate, let's say, 1 for 3 and -1 for 8, and you're going to see why. Okay, so I'll let you read this if you haven't yet. I'll give you 5 minutes, and if you have questions, let me know. And then we move to coding. Okay. Not a single question, so I guess you're completely lost.
I was waiting for you to be done. I did have a question.
Uh-huh.
It looks like there are 2 for loops up there, but I don't understand what ranges we're looking at for I and J.
Which one? Okay,
So it looks like...
so I refers to the sample. So basically we have m samples,
So wait, M?
like lowercase m.
Oh, so it's just the number of samples, and
Yeah.
then J is each...
J is what we use for the weak learner. Okay?
Okay.
Yeah. So I is used for samples and J is used for learners. All right. Let's implement this. And okay, one. Yeah, I'm not sure I can have 2 projections at the same time. Anyway, we'll think about it later. Okay. So here we start with all samples being equal. We're not discriminating against any one of those, and then we're gonna implement one at a time. So let's start with the samples, and let's start with initializing our weights. Okay. So we go to the fit method. Okay. So let's start with our weights. So in this case, we're gonna just do, it's gonna be NP once, and then you're gonna be X train that shape, or just do Y train that shape, right? Okay, and then we can just divide by Y train that shape 0. Okay, this is the number of samples when divide by those. So those are our weights. Okay. Perfect. So now we're going to start our rounds. We have n rounds, or n learners. So let's do for I in range, self n learners. So now we're going to train the first learner, all right? And this is provided by the argument self base. So this is a function that will generate our weak learner. So we're going to do self base. Perfect. Okay. Now we're just going to fit this learner. Fit X train while Y train. But we have to provide the weight associated with each sample, okay? And if I'm not mistaken, if I go to sklearn, decision tree classifier, in fact, all classifiers are going to have a parameter called samples weight, not class weight, max features, nope. It's going to be in the fit method. There you go. So you have sample weight. Okay. If you're wondering what that is, I can explain later. So those are our weights. Perfect. Okay. Now I can predict to see which samples I have misclassified. So I can do pred equal learner dot predict and my X train. All right. So now I'm going to have some samples that are misclassified. So I have to basically update the weights associated with the samples. So initially, I have to compute what we call error rate. Okay. This is the AdaBoost algorithm. So we have to compute this one. Okay. And the error rate is specific to each learner. So we're going to need it, right? So what happens here is that we just take the weights that you have in W and multiply them by what you call delta. So delta y pred is equal 1 when they are different and 0 otherwise. So the weight is going to be constant if the sample is not misclassified, it's correctly classified. And, sorry, it's going to be zeroed out You're going to zero out the weights of the samples that were correctly classified, so we're just going to ignore them. So we're only going to keep those that were incorrectly misclassified, okay? So that's what I'm going to do. And let's look here. So that's the method error rate. So I have y true, y pred, and weights, okay? So what happens here is that I'm taking weights. I'm going to multiply it by y true different than y pred. So here's going to be true, false. Sorry, the false is treated as 0, true is treated as 1. So this is true when they are different and 0 otherwise, okay? So let's call these total. Okay. And now the error rate is going to be the total divided by the sum of the weights. Okay, what's the ratio of weights that were misclassified? And that's my error rate, okay? And return, let's just do it here. I'm gonna just check again that what I'm doing is correct. So I trained it using the current weights that I have. I predicted on the samples, and then I computed epsilon j, right? So the error rate here, we're just counting was the ratio of the weights associated with samples that were misclassified. Perfect. Now I'm going to compute what we call alpha. So alpha is the weight that I'm going to associate with the learner. So the higher the alpha, the more important the learner is, okay? And here, k is the number of classes. So this is the algorithm that you're going to use in multi-class. So if you have like 4 classes, then the k is going to be 4, and you're going to have -1, so it's going to be 0, okay? So in this case, it's binary classification, so k equals 2, and log 1 is 0. So we're just going to ignore that log thing since we have a binary classification, okay? And the thing I mentioned is that for AdaBoost, you don't want a consistent classifier on the training data. So if you remember homework 1, we have a bonus question that says that a consistent classifier in training data is a classifier that will give you 100% accuracy on the training data, which is the case, for example, KNN with k equal 1, you can always have 100% accuracy. So for AdaBoost, for example, you don't want to use KNN with k equal 1. Why? Because in that case, the error rate on the training data is going to be 0, and you don't want to divide by 0. That's just math 101. All right, so now we have the error rate, so we're going to compute the alpha j, the associated with the learner, okay? And that's basically what we are going to store in self.alpha, okay? So we have error, self, error rate of y train, y pred, and weight. Perfect. And now my alpha, self alpha j, is going to be equal to mp.log. You can use 2 or any other factor, just multiplying by a constant, and it doesn't matter. You can multiply all alphas by the same constant. It should not affect the votes. All right, so now we have our alpha j's, but now we have to go back and update the weights, right? So if the sample is classified correctly, then the weight is going to be 0. We're going to multiply by 1. It's going to be exponential 0, which is 1. If the weight was, if the sample was misclassified, we're going to multiply by exponential alpha j. So that's the constant that we are going to multiply with, okay? And so what can we say here? What can we say here? Well, alpha j is always greater than 0, so exponential alpha j is always going to be greater than 1, okay? You can prove that this quantity can be, when alpha j is lower than 50%, right? If it's lower than 50%, you can show that alpha j is greater than 0. Yeah. So the log of some value that's greater than 1 is going to be greater than 0. So exponential of a value greater than 0 is going to be greater than 1. So w is going to be crazy. Okay. All right, so let's do this. We're going to just change the weights. We're going to update the weights using this alpha j that we just computed. So now the weights is going to be equal to the weights multiplied by the exponential of the alpha that we just computed. So just to be consistent, I'm going to call it j here. Since we said we're going to use j for the learner. Perfect. And here's going to be the same thing that we have done before, which is y-train different than y-pred. So if they are equal, it's going to be 0, and the weights are not going to change. And now we just have to normalize to have sum 1. So it's going to be weights divided by NP sum of weights. All right, so now we have new weights, and the same thing repeats again until we have everything we need. One thing that we have forgot to do is that we didn't keep track of the learner, okay? We want to save the learners. So once we have that, we're just going to do self learners append learner. So this is basically AdaBoost. There you go. It's as simple as that. And you can see it's the same thing for multi-class. You just have to take care of that log k minus 1. But the trick is in the predict. For us, it's going to be much easier. So you're going to see how to work with that. All right. So one thing here is that we can compute the score at the end of each iteration. So that's we're going to do it later because we still have to implement the predict method. Okay. And if you remember correctly, we had the labels are either -1 or 1. Okay. So in the prediction method, where is it? Yeah. This is our prediction, okay? So we're going to predict from each learner that we have, multiplied by its corresponding alpha j, and then we're going to have h. So some alpha j's are floats. We're going to have the sum is going to be float. But if the quantity is lower than 0, then it means -1. If it's greater than 0, it means that it's going to be equal to 1. Multi-class, you can't just use -1, 1. You have to be a bit creative to do it for multi-class. But for now, let's just take care of the binary classification, okay? So we're going to predict. I have my x here. So what's the easiest way to do it? Yeah, let's just do it the lazy way, okay? So let's do y-pred equal NP zeros, x train, let's shape 0. It's not x train, just x, okay? And then I can do for alpha learner in zip self alphas self learners. Going to do y-pred plus alpha multiplied by learner predict x. Okay. So the label is going to be just the sign. So I'm going to do return NP sign of y-pred. Okay, so now that I have predict, I can just go here in my training, and let's call these yeah. Actually, the solution is already in stage score. So if you understand this one, you're going to get the solution for predict, so that's not a problem. Okay, so I guess now we're done with our AdaBoost, right? Oh, we have a divide by 0. Oops. So we have same array element with the sequence. Okay, I have an error here. So the error rate is returning. It's not returning. Yep. So the error rate is wrong because it's returning an array. So I have to do npSum. There you go. So here I just did 3 rounds. Okay. And it makes sense that the alpha are going to be increasing. That's the alpha for each one of the 3 rounds that I have. Okay. Yeah, we're done with the fit, we're done with the predict.
What did you change in that array again?
So the array rate returns an array, it should return a float. So I did npSum of total.
Okay.
Right, because if you go to the form for the algorithm, array rate is the sum. I forgot the sum in the denominator. Perfect. Okay, I don't remember this exactly, so let's just hope I get it correct. I have no idea, but let me just check. I think NumPy mesh grid. Yeah, I guess I need the mesh grid in this case. All right, let me do it here. It has no attribute alpha. Okay, I did an error here. Yeah, I have to use self.alpha, not alphas. So in the predict method, there you go. All right. So this is basically just my, on this toy data set. Okay. Let's do something here. So I used, as classifier, I used my AdaBoost here. Okay. So one thing is, let's see, I'm not going to use self-classifier, I'm going to use learners 0. That's the first learner. That's exactly what it does, okay? And I can just make it a little bit clearer. I can do x scatter x 0 1. Let's see. Yeah. So this is my first learner. This is my first decision stump. So just gets 2 correct. Let's move at the second one. This is my second learner. All right. So the first one will get those 3 incorrect. Okay. That's what happens. It gets those correct, but it gets all those 3 correct. So the second learner now, it ignores the other 2 because those we got correct. So now it goes to the other 3. So now you have the other 3. Okay. Now the second one is getting these 2 incorrect. So now we have to go back and give them more importance. So let's see what's the third one is doing. Yeah. So now it's got just the 5 yellows as correctly. Okay. And if we increase the rounds, I would assume the fourth one is going to predict these correct. So let's just do 4 rounds and see what we get. Let me do here, I'm just guessing. You can bet. Let me do 3 here. Oops. So the third one does exactly like the first one. Okay. So it's basically a back and forth. All right. Okay, so now let's just keep this one here. So 3 and 4 does not change anything. Since 3, we already get everything correct. Okay. So there's the method that's called scored stage score. So let's do CLF stage score x and y. Yeah, so just giving me the error or the accuracy that I get after each round. So the first one, I'm missing, I guess, 3 out of 10, something like that. yeah, I was missing 3 out of 10, so it's 7. By the third round, I'm getting perfect accuracy, so the error rate is not going to change anything. I'm just kind of training something that I already have. Okay. Perfect. Now let's go back to our decision, our digits data set, okay? So now it's 300 rounds. In this case, you just hope your code is efficient, otherwise it's going to take minutes. But let's see. All right, perfect. All right. So this is the error rate. Remember, we started with 85% accuracy, which means 15% error, misclassification error. And okay, so the train is overfitting. You see that the gap between validation and trading increases as we increase boosting iterations. So when the number of learners is too large, we're basically getting more overfitting. Okay, but we're still doing better than a single weak learner, which is the decision stop. We move from 15% to around 4%, so that's basically 96% accuracy. All right, but then you can also always try to compromise between running time and, yeah, let's say like between 300 and 150, probably reducing the error rate by 1%. So you can always choose how expensive or how much you want to pay for the additional accuracy. Yeah.
When you're looking for some minimum in that graph, how do you avoid getting those local minimum spiky boys that we see all scattered over it?
Good question. How do you avoid those bumps? I'm guessing because decision tree is kind of random. Yeah. You have a question? Okay, so let's try just go to our base, the function here, and let's change. So here we have base max depth. I'm just going to change random state to 42. I'm just going to fix the randomness and see what I get. Nope, it's still noisy. Yeah. But the intuition here is that, as you've seen here, we just have these back and forth between the weights. So sometimes when you add a new learner, it will sacrifice few samples to get other ones correct. So that's why you have those small bumps. That's just my guess. If you want to make sure, we can, okay, let's do stage score on this one, okay? Let's plot this one. Yeah, these are the alphas associated with each learner. Okay, but let's do CLF, staged score between data, X valid. Let's do train, because train is basically what you train on. So we should have more consistency. And make it simple, let's just do plot. BLT the plot. Yeah, so in the training data, as the algorithm actually works, so it's not strictly increasing. We have some regions where it's kind of flat or even decreases, but asymptotically, it's going to always increase. All right. Is it clear or need more explaining?
You scroll back up to where you had z equals CLF dot learners dot predict from.
When I was using learner?
Oh, yeah.
So that one, I was just looking at the learners themselves. Okay. So, for example, the first one, I was just looking at the decision surface. Oops. Oh, I haven't defined. Okay. Yeah, I was just looking at a single learner.
Okay.
Yeah. And what we showed is that once you get 100% accuracy on the training data, the fourth one is exactly like the first one. It's not. We're not learning anything different. I can even go to 5, and I'm guessing the same thing is going to be repeated. But let's look at. So 5 is going to be like the second one.
And what is that access parameter if you're passing to It's like access is the only one.
Which one?
Access.
Yeah, so this is a mesh grid. So if you look at the mesh grid, it's going to give you 2 matrices. All right. So the first, like 0, 0 of the first matrix is the x coordinate, and for the other matrix is going to be the y coordinate. So what I'm doing here is that I want the first coordinates or the x coordinates to be the first column, and the y coordinates to be the second column. So just reshaping and concatenating them column-wise. Okay, and then doing the prediction. All right, all clear? Okay. So homework 2 is, I think, a bit more challenging than homework 1. So the earlier you start, the better. And you're going to implement decision tree from scratch. And so there's a variation from scikit-learn. Scikit-learn uses the Gini index by default that we have seen last time. The one in homework, we're going to use entropy. So if you didn't compare to scikit-learn, just use Gini and see what you get. And on scikit-learn, there's a randomness. So for us, we just we do this in order. We go through each feature, through each threshold, and then we take the best one. But for scikit-learn, it's going to be doing some shuffling. So if you have 2 features that give you the same reduction, scikit-learn might use different one than the one you have. So if you get different features but the same values of reduction, don't panic. It's just the randomness in scikit-learn. Okay. All right. Good luck.